Okay, we're going to take this opportunity to review what we did today as we talked predominantly about the field command, but we're going to kind of do this in the review process here with the inking bit. And that was this basically the set of equations that are fundamental to structural stuff as we go into Inventor and some of these other modeling programs that do finite analysis and the like. We cannot forget that, in fact, the father or the mother or whatever you're going to call it of all equations is the shape equation. 1 over rho, which is the radius of curvature, is equal to the moment divided by the modulus of elasticity of the material times the second moment of the area. And if you can think about this, that basically this thing is going to be bent depending how much bending is involved and how resistant it is to bending. So, and we're going to let you know that this equation combined with, right, boundary conditions, right, like a cantilever here is going to have a boundary condition that it's going to be fixed and it's not going to be able to rotate or translate, or in effect a simple support there, if you would, is going to be bound by an ability 1 degree of freedom here and 2 degrees of freedom here. So that general sense that this equation and boundary conditions is going to eventually get you into that structure. It's going to get you potentially the force inside of it, the moment inside of it, and the shear force inside of it. So this concept that it's what's pushing on it and how it's held that makes the internal forces, moments, and shears come in. All right, and so we then got to the basic equations that we know or should be exposed to. Is that first, that the actual axial stress is equal to the force over the area, said force being the force into the plane. We also saw that the bending stress is equal to the moment, the internal moment at the section times the half depth of the beam divided by the fake moment of inertia or the second moment of the area. And we saw that the bending stress distributes, if you've basically got something along here and cut a cross section across it, the bending stress in a beam that's got a positive moment on it, positive causing compression in the top, is going to be compression in the top and tension in the bottom. So this idea that you're going to have a set of equal and opposite non-concurrent forces that cause a moment, they're separated by a distance d, and the moment is equal to fd, basically. And so this is what occurs in bending. You know you have no bending stress at the middle, at the neutral axis, and you have maximum on either side. We also saw then the shear stress distributes differently than this, and it is equal to the shear force times the first moment of the area divided by the second moment of the entire area and times the width at the section that you're talking about. And we saw that we know what the second moment of the area is, but if we looked at a beam here, right, that was 2 by 10, and it was subject to a force of 1,000 pounds, and we were interested, for instance, at perhaps what is the shear stress at the middle here. What we did, we took 1,000 pounds times the first moment of the area, which is 2 times 5, times the area to the centroid, 2 times 5, which is that area here, times 5 is 10, times 2.5, that's the area of the centroid there. And so that would be 25. Right, and that of course is inches to the third because it's area times distance, divided by the second moment of the area, which would be bh cubed over 12, which we said was 166, and then the width was 2 inches, and we got something like a stress of 75 in there. And so we notice that here that would be, if you look at the shear stress distributed across the face, the shear stress looks like that with a relative maximum right there. And of course the shear we're going to see is going to be something shear. If we remember about Mohr circle here, Mohr circle shear in this direction along one face is going to cause an equal and opposite along the other set of faces. And so we had that idea of Mohr circle. So one more time with 5 minutes, I'm going to write these out a little bit neater, and we're going to go to here to a new blank screen, and we're there, and I'm going to write them out one more time with review. You should be able to do this just as fast. 1 over rho equals m over EI, with I being the fake moment of inertia. The axial stress is equal to P over A. In other words, if you have something here with a longitudinal force P across it, you can cut it at a point here. And when you cut it, if you would have something here with a force P, and here you would have a stress P over A. This would be what? The sum of the forces equals 0, because this is P over A times A, and therefore P equals P. You know that the bending stress is equal to MC over I, with C being the distance from the neutral axis. And so we have here, if we cut a beam, it is perhaps subject to some twisting moment here and a twisting moment here internal that comes into basically into an area of compression and an area of tension. We take the area under the triangle, you put it right there, and essentially what you got is a compressive and a tensile force in two different faces, and you know that the moment is equal to this distance between them times the force of any one. That is the bending stress and how it distributes across. Then we looked at the shear stress. V is usually the sign for shear. We take the shear force divided by the first moment of the area above the place that you're worried about, divide the moment of inertia of the whole section times the B. If you in fact had some otter shape, it looks something like this, right? If you were interested in actually the stress right there, you would take the shear, and then you would take the moment of the area on the outside, which would be this area, times this distance, divided by the moment of inertia, which you probably would look up. We'll talk about how you do that, and then the width at that point right there. Now, I pointed out in class that the moment of inertia, the fake moment of inertia, the second polar or second moment of the area for a rectangle is equal to BH cubed over 12. That should go in your head. You can basically, I talked about in class as well, that no matter what shape you have, you can break it up into strips. And that's essentially what calculus is. When you're looking at the calculus here, in other words, you take the BH cubed over 12 for that one, the BH cubed for 12 for that one, and the whole thing. Or in the end, another way to go about doing this we'll see is the idea of taking that area times this distance squared plus this area times this distance squared. So there's a couple different ways to get your moments of inertia on shapes. Mass prop, of course. We remember that we can get mass prop in AutoCAD. We'll get us the moment of inertia, but we must move the centroid to 0, 0 or 0, 0 to the centroid. All right, I'm going to go ahead and get another sheet here. Quickly review what we talked about in terms of field command. If in fact we are once again in review, start inking. I have a tower here. I'm going to put a tower with a couple of cantilevers out on it. I guess I don't have a couple choices. I think I do. A couple cantilevers there. In this pen I can change the color, I think. Can I? Oh, it doesn't let me. All right, it doesn't let me change the color. That's fine. So what we've got here, let's say this is a bending, this is something that's in a, it's a cantilever, more or less it's a fixed connection. We know how we solve for the reactions and everything else, but we know that the sum of the, if we look at our free body diagram with we have a force here and maybe a force here. If we want to do the free body diagram of this whole thing, we replace this with an unknown force there, an unknown force here, and an unknown moment there. If we want to get this moment here, that moment inside the structure is going to be equal to the, if I cut it right above here, it's going to be equal to the moments of the forces that were applied there. And so if you call this force 1, sorry, that's my radial vector, and that's my force vector. And I call this my second radial vector and my second force vector. We can tell you that the internal moment here is equal to the opposite of the sum of R cross F, where I equals 1 to, when N equals 1 to 2. In fact, we've only got 2 forces. But if we start adding up other forces in different spots, we just continue to add radial vectors. That is what we use the field command for, to get the reaction. But in addition, as we move our way up the structure, that radial vector is changing, and so we can calculate the internal moment and the internal shear and the internal force at any point in the structure by using the field command. And that's what Inventor essentially is doing. Thanks for listening. Hope that was the whole class in 10 minutes. So those who missed, I guess you're covered. Thanks for listening.